Okay, Bismillahirrahmanirrahim. Welcome to class of Irrigation Engineering for 30th April. Good number of students are with me, 32 students are with me. I have already shared my screen. Hopefully you are seeing whatever I am saying on my screen. Last time we started with the topic of crop water requirement, and we have gone through the first few slides. Tell us why we have to study this need of studying the concept of crop water requirement, and we have found that it has relationship with the planning of an irrigation system, with the execution of irrigation system, execution of irrigation practice. For example, if we have to give water to some farmer, so that is a execution of irrigation practice, carrying out irrigation itself. So if we want to provide water as per demand of the farmers, then crop water requirements should be known to us. Similarly, if you are farmer yourself and if you want to apply water on scientific basis, then crop water requirement and its concept should be known to you. How much is the evapotranspiration requirement? How much are the losses? How much is the special needs? So basic necessities which make this topic important were informed to you. Then different groups of methods were informed to you. Before that, factors affecting crop water requirement were informed to you. Then we grouped methods of estimation of crop water requirement, or consumptive use, or evapotranspiration requirement. Calculation of evapotranspiration requirement or its measurement in the field. Those methods were grouped into three categories, 3 or 4 categories, and I think three methods were informed to you. One was based upon the physical experiment in the field, and the instrument which was used, we call that as lysimeter. Using the lysimeter, we can carry out assessment of. Please hold a minute. There is a visitor in the room. Okay. So we informed you a method for estimation of crop water requirement with the help of lysimeter. And anybody will tell me what was the concept of lysimeter, how we can find evapotranspiration using lysimeter. कोई बच्चा बताएगा मुझे? Anybody will like to share his thoughts about lysimeter? Ahmed Al-Azim. Ahmed Al-Azim. No response. So I am removing you, Ahmed, from the class. Ahmed, no response, no listening, no trial to response. Okay. Shehbaz Zafar. Shehbaz Zafar. He has removed himself. Okay, when he joined back, please tell me. What is the problem? So yes, Shehbaz Zafar, you have raised your hand. Please unmute your mic and tell me what is the concept of lysimeter. You have raised your hand. I did not ask you to raise your hand. He has given in writing something. I am from Kashmir here. Internet is not good quality, so can't speak in voice call. Very good. Okay, write down your response. Shabazz, write down your response. And if you are not getting my voice or I cannot get your voice, it means you are not attending a class. If there is a communication problem, those people who have communication problem, they are living in the hostel. So Shabazz, I'm not happy. Asad Ijaz. Asad Ijaz. Muhammad Asad Ijaz.
Yes, sir.
How are you?
Alhamdulillah, sir.
ठीक हो?
Yes, sir.
नाश्ता किया हुआ है?
No, sir.
क्या वजह, अम्मी से बनी हुई नहीं है?
No, sir. 9 से 10 ब्रेक है तो उसके अंदर करना है.
Okay, okay. So we were talking about lysimeter.
Yes, sir.
तो क्या होता है lysimeter? किसी को बताना हो, अपने इलेक्ट्रिकल के दोस्त को बताना हो तो क्या बताओ?
सर अभी लास्ट लेक्चर मैंने ले नहीं सका था तो इसलिए आइडिया नहीं है.
मोस्टली जिनसे मैं पूछता हूँ वो यही क्यों जवाब आता
सर आई डोंट नो सर, मैं लास्ट
है?
लेक्चर ले नहीं सका था इसलिए आइडिया नहीं है.
नोमान भट्टी, नोमान अली भट्टी.
Yes, sir.
How are you?
Assalamu alaikum, sir.
Yeah.
Alhamdulillah, sir. Fine.
Can you describe what is a lysimeter and what is a concept which we use to find the evapotranspiration requirement using lysimeter?
सर लाइसीमीटर का मैंने जो मतलब लास्ट टाइम पढ़ा था उस हिसाब से इसके 3 मेथड्स थे. फील्ड एक्सपेरिमेंटेशन, इनफ्लो, आउटफ्लो. तीसरा भी था, मुझे एग्जैक्टली याद नहीं. तो ये कोई कंटेनर होता है जो मतलब हम इंस्टॉल करते हैं फील्ड में, जो मतलब सेम क्रॉप्स होती हैं जहाँ पर, क्योंकि वहाँ पर इवेपोट्रांसपिरेशन रेट जो है सेम होगा उन क्रॉप्स की नेचर के हिसाब से. This is all I know, actually.
So at least you have told me that it is like a container. This is an instrument like a container and it is installed in the field environment similar to where actual crop is grown, so that evapotranspiration requirement should be same. That's true. But the first part was not true. That lysimeter also includes field, what we call it, field methods, inflow, outflow. So those three methods were parallel to lysimeter. So lysimeter is itself a method which we use as mass balance method. In the group of mass balance method, our direct method, we measure evapotranspiration. So it is true, lysimeter is a container. We install it in the field, and we install, after installation, we fill it with the same soil as the surrounding soil. We plant the same crop as the surrounding crop, and it should be the crop of our interest for which we want to measure evapotranspiration. Then we carry out the measurement of inflow of water to the lysimeter and outflow of the water from the lysimeter. These things we carry out, and of course we take into account the inflow through irrigation, inflow through precipitation, and outflow from the surface runoff from the lysimeter, outflow from the deep percolation, and also we take into account if there is any change of the soil moisture within the lysimeter. So these things we carry out, these measurement we carry out either on daily basis or on seasonal basis, depending upon our requirement. And from these measurement, then applying the mass balance equation, which says that the total inflow should be equal to total outflow between two time steps plus change in storage in the soil. So applying that equation, in that equation all things are measured except the evapotranspiration. So ET we calculate from that equation. Okay. So let us move ahead. Today, what we want to go through, if anybody having questions, you are welcome to ask. किसी के कोई सवाल है तो आप इस वक्त this is the time. Anybody having questions? Mohsin Hanif.
Yes, sir.
Mohsin Hanif. Other than lysing method, two other methods we studied. वो क्या थे?
Sir, pan evaporator
Pan evapometer. एक और तीसरा method we studied.
and sir, empirical methods.
उसका नाम क्या था? empirical तो बहुत सारे हैं.
Yes, sir.
There are many methods. So one particular method we used it and solved an example also. What was that method?
Sir, वो याद नहीं.
If I tell you the first part, Blaney, BLANEY something, Blaney. Second part, you remember?
Sir, Blaney cradle, I guess.
हाँ जी, Blaney cradle method. That's right. These are the new terminology for you people. Till you don't use them, you will not be familiar with them. Please use it and make it part of your discussion so that it should not be something something aloof, something new to you. You should be familiar with this. Musa Kakar Sahab, Musa Gul Kakar.
Yes, sir.
How are you?
ठीक sir, alhamdulillah.
Okay. In Blaney-Cradle method, there were two parameters used to calculate the evapotranspiration. Can you tell me what are the two parameters in Blaney-Cradle method?
सर ये मेथड अभी डिटेल में सर पढ़ा नहीं है आगे.
अगर सिर्फ लेक्चर ही सुन लेते तो पता चल जाता. असद इजाज.
सर लेक्चर लिया सर अभी.
Asad Ijaz. Okay, thank you, Kakar sir.
Yes, sir.
For not studying. Asad Ijaz, same question to you.
सर मैंने आपसे एक्सक्यूज की थी कि लेक्चर मैंने लास्ट ले सका था.
असद इजाज. और आपको मैंने बाहर निकाला था?
नो सर.
ओके, उसामा. Usama. Roll number 24. 2017 Civil 24.
Yes, sir.
Same question to you. What are the two parameters used to calculate evapotranspiration using Blaney-Cradle? To use the
सर मुझे अभी याद नहीं आ रहा.
तुम उठ तो जाओ बेटे. तुम्हारी जो आवाज लग रही है अभी तो तुमने लगता है मैंने क्या कहते हैं वीडियो ऑन करवा देनी है आपकी.
सर वो अभी लेक्चर रिवाइज नहीं किया.
लेक्चर तो कर लेना लेकिन उठ तो जाओ ना.
ओके सर.
ओके, मुझे नहीं लगता आप लोग कुछ साथ चल रहे हो. तो let me ask the volunteers rather than asking the people. Who will tell me? Raise your hand. so that I should have a little bit confidence that somebody is with me. Anybody raise your hand? What are the two factors used in Blank riddle? Thanks. There is roll number 16 and 36. So one factor 16, you tell me please.
अस्सलाम वालेकुम सर।
वालेकुम 16 दो सेट फैक्टर है, उनमें से एक का फैक्टर का नाम बता दो।
यस सर, एक मंथली डे लाइट आवर्स है उसके अंदर।
So percentage of the daylight hours with respect to the annual daylight hours. Thank you. And it will be monthly if you are working with the Blank riddle on monthly basis. But if you are working with the Blank riddle on daily basis, it should be the daily daylight hour percentage with respect to the annual daylight percentage. Thank you. 36 अपना नाम भी बताओ और सेकंड फैक्टर भी बताओ।
सर जुहेब सुल्तान नाम है सर। टेम्परेचर है आई थिंक।
Temperature, so mean temperature of the time period. If you are working on monthly basis, so mean monthly temperature, and if you are working on daily temperature. So thanks. So that is a quick revision. Soil water plant relationship is also important so that we can use the water. Okay, and I have added this one more slide in my slides. Last time some student asked me, sir, where is the evapotranspiration requirement? You are showing us the evapotranspiration requirement for other countries like India and this. Nobody have carried out study. So this is the reference of the study carried out by PCRWR, Pakistan Council of Research and Water Resources. They use the lysimeter, I think, in Faisalabad or Lahore, this is central Punjab, and they calculated the evapotranspiration for wheat as 421 centimeter, 421 millimeter, 42 centimeter. So from there they calculated the KCs for wheat in this area. Similarly for rice, for sugarcane, and for other crops they have carried out. So this is not present in your slides which are given to you, but you can use it from here, and maybe next time when I share, so this will go with to you because recording will be with you, so you can see this slide in the recording. Soil water plant relationship help us know the behavior of the soil with respect to its usage of water, behavior of soil with respect to its with respect to making water available to the plant. So there are different soils which can absorb water in a different way. So that will help us, and there are few terminology which is necessary to understand the water retained by the soil and water released by the soil, and there are different moisture contents. Their nomenclature should be known to us. Moisture content, you know, is a representation of how much water is there in the soil, and you have carried out experiment in the geotech or soil mechanics laboratory in which you have measured the moisture content of soil using the oven method, using the you put the soil sample in oven for 24 hours and then deducted the weight after the oven drying and before the oven drying. So that difference was the mass of the water. You divided it with the mass of the soil, and the ratio was the moisture content. So moisture content value you can measure in the soil at different stages. One immediately after the watering, one after few days, one when you see soil is close to dryness or totally dry. So there are different level of moisture content. There are different quantity of moisture content. So these levels with respect to agriculture, these levels of moisture content are these borders of the moisture content have been given different names. So those names will be informed to you in this lecture, in this few slides. With respect to retainability of the soil, with respect to water retention capability of the soil, there are these three moisture contents, are these three level of moisture in the soil which we should be knowing. For example, one thing we call is the gravitational moisture in the soil. When we apply water to the soil or when there is a rainfall, when rainfall occurred in sufficient quantity on the soil, then soil becomes saturated, and if it is water is more than saturation, then runoff starts. So after the saturation of the soil, after a few days, some waters drain out of the soil under the action of the gravity. It goes out of the soil mass, it goes out of the soil body under the action of the gravity and goes to the deeper layers until it reaches to the water table or lower layers. So that water which escapes from the soil under the action of the gravity, that water we say that this is the gravitational water, and or we say this is a gravitational moisture. So when water is applied on a field, a part of it gets absorbed in the root zone and the rest flows downward under the action of the gravity. The water which flows downward under the action of the gravity, that we call as a gravitational moisture. And the remaining moisture, we consider that is the usable water. So gravitational moisture which leaves the soil in a couple of days, we consider that water as not available to plant for its nourishment, because in short duration it leaves the soil under the action of the gravity. So after the gravitational moisture is gone out of the soil, so then rest of the moisture, whatever it is, and if we measure that, we call that moisture as a capillary moisture, or sometimes we call it moisture content at the field capacity. Both are the similar concept. So moisture content after all the gravity moisture has been gone. Soil water content or moisture content when gravity drainage becomes negligible. So when gravitational moisture have already escaped from the soil, so then whatever moisture is left in the soil, if we measure that, so that one is called as the field capacity. And usually moisture content is represented in literature most of the time with the symbol theta. So theta with the subscript Fc represents field capacity moisture content. And sometimes we simply use field capacity Fc as a symbol. So it is simply moisture content once gravitational water has escaped from the soil. So then the moisture content of the soil is called as the field capacity. This is important with respect to irrigation. We should apply that much water to the soil which bring the moisture content to the field capacity, not above that, not beyond that, because any moisture beyond field capacity, above the field capacity, that will be wasted as a gravitational water. So for agriculture, gravitational moisture is a kind of wastage, because it remains within the soil for a couple of days and crop cannot get that water on a long-term basis. So this field capacity moisture is held within the soil because of the capillary or because of the surface tension of the water. So it remains over there. Although gravity is trying to pull it down, gravity is trying to extract it down, but because of the surface tension and its adhesion with the soil particles and because of the capillary action, it remains within the soil. So that quantity of moisture, if I measure, which remains within the soil against the against the pull of the gravity, it remains within the soil. So that is called as a field capacity. Why it is important for us? Because as agriculture or irrigation engineer, when you want to apply water, you should try to reach to field capacity, not beyond that, not to the saturation level, not to the runoff level. So we have to put that much water which just fill the soil pores up to the field capacity moisture content. So that is its importance for us. So that's why it is being informed to you. So you should be knowing what is the field capacity. It is a well moist soil, and in a simple way, after application of irrigation or after the rainfall, the condition of the soil after 2 to 3 days after rainfall, after 2 to 3 days, that represents the moisture content at field capacity. Scientifically, if you measure it in the laboratory or in the field using the pressure meter, not the pressure gauge like Borden gauge in our laboratory. So we have some pressure measurement device to measure the negative pressure or tension in the soil. So you have to understand this tension in the soil. It is not tension load like you apply on the steel rods. It is like a ability of the soil to attract water. So if you soak a soil, if you make a soil wet, and when it is fully saturated, when the soil is fully saturated, then we say it has no tension. It has the same pressure as the atmospheric pressure at the saturation level. When soil is saturated, we say the pressure within the soil is at the atmospheric pressure, or it has no pressure with respect to the gauge. Uh, so when it is saturated, no pressure. So when soil gets dry, when it goes towards field capacity or towards the dryness, then it has some tendency to attract water because of the capillary action. So that tension is called as soil tension, and we have tensometer available which can measure this lack of pressure or this lower pressure. So if we want to measure the soil moisture tension within the soil, so at the moisture content equal to the field capacity, soil show a water potential or soil water tension equal to 0.1 bar up to zero point 0.3 bar. So negative 0.1 bar to negative 0.3 bar. So negative shows the lower pressure, lower than the atmospheric pressure. So we call it as a soil water potential or soil water tension. So field capacity represents the water content in the soil at a water potential of 0.1 to 0.3 bar. So if you have a tensometer installed in the soil, so when it is fully saturated, it will show zero pressure. So when it goes towards dryness, then it will show negative side pressure. So when field capacity moisture content reach, at that time the soil tension is close to this value 0.1 bar to 0.3 bar. So that is the scientifically way of representation of field capacity. The moisture content corresponding to soil water potential equal to 0.1 to zero point 0.3 bars. And you know bar is 10 raised to power 5 Pascal. And Pascal you know is Newton per meter square. So normally atmospheric pressure we say is 101 kilopascal with respect to absolute zero. But with respect to gauge pressure, this 101 kilopascal is said to be equal to zero. So below that atmospheric pressure, it goes to zero point 0.1 bar. So keep this thing in mind. I have told you two methods how to get the idea about the field capacity. One with respect to application of water, and after 2 to 3 days, whatever be the moisture condition in the soil, that is closely resembling to field capacity. Second thing is if you have some instrument to measure the pressure in the soil on the negative side especially. So there are gauges which can measure positive pressure, which can measure negative pressure. We call them as a vacuum gauge. So you should have a tensometer which can measure the tension in the soil or negative pressure in the soil. So when it shows minus 0.1 bar to 0.3 bar, so at that time if you measure the soil moisture content, that you can say this is the field capacity of the soil. Different soil have different field capacity depending upon their porosity, depending upon their attraction with the water. So sand will have different field capacity, clay will have different field capacity, and loam. Loam is the soil which we say it is a mixture of clay, silt, and sand. Mixture of clay, silt, and sand, or we say this is loam. Agriculture wise, this is considered to be good because it has a good field capacity level and it has good moisture available for the plants. So after we understand what is the gravitational moisture, after we know what is the field capacity, another important thing is called as the moisture content with respect to the condition when plant cannot extract water from the soil. There is a plant get water from the soil through capillary action. It pulls the water because it has some shortage of the water in the leaves, and when leaves are in shortage of water, they pull the water in the stem, and then that pull the water in the roots. So it is the osmosis or the capillary pull which is taking water from the soil up to the leaf of the plant. So when that pull is not sufficient to extract the water from the soil, then water is not reaching to the plant and the leaves of the plant wilt down. They go down. Wilting occurs over there. Simple हम उसे कहते हैं मुरझा गया है. So that moisture content, after which plant will not be able to extract water from the soil. So that moisture content will be called as wilting point. So that will be represented by theta WP. So soil water content below which plants cannot recover from water stress even if placed in humid environment. So after wilting, plant nourishment, plant growth is affected, and even afterward, if I place it in a very humid condition, its yield, its output will not be same as the plant which has not reached to the wilting point. So this permanent wilting point is that point after which yield will be affected even if I give it water later on. Although at this condition, when wilting point moisture content is there, there is some quantity of water present in the soil, but it is so tightly or so strongly bound with the soil that the plant cannot extract it. So to extract that water content, we have to put that soil under a high pressure, under a high vacuum pressure, or we have to put that soil into the oven so that that moisture content should also be taken out of the. But plant cannot take water when it moisture content reaches to wilting point. So hopefully you understand that field capacity moisture content will be higher and wilting point moisture content will be lower. Still there will be some moisture. It is not zero moisture in the soil. Scientifically, if I am carrying out experiment in the laboratory, so the moisture content corresponding to minus 15 bar soil water potential. When I apply a vacuum pressure or negative pressure of soil at the soil equal to minus 15 bar, so then most of the water will be going out of the outer soil because of this vacuum pressure. So then the remaining moisture content which still remains within the soil, so that will be called as wilting point or permanent wilting point. Similar concept with respect to previous one, as I told you, field capacity. So relevant to field capacity, we call another terminology, we call it as a capillary moisture. So field capacity is further divided into two types. One is called as the capillary moisture and one is called as hygroscopic moisture. So whatever was the moisture content at the field capacity level, we can divide it into two parts. One, moisture which is within the capillaries, which is retained within the soil because of the capillary action, and one moisture which is retained within the soil because of the loose chemical bonds. So field capacity moisture remains within the soil because of the two actions, one because of the surface tension or capillary action, and one because of the chemical bond. So both of these. So this hygroscopic moisture cannot be taken out by the plant. So this is not available. So this corresponds to something wilting point. It is not exactly the wilting point, but it is close to that wilting point. And this capillary moisture is considered available to the plants. This is considered available to plant. plant can easily extract this capillary moisture. Permanent wilting point, the moisture content of soil at which plant can no longer extract, we have already. So this from this capillary moisture and the concept of the wilting or hygroscopic moisture, we can find the moisture content which is actually available for soil. It is a difference in the moisture content between field capacity and the wilting point. So field capacity moisture content or wilting point moisture content, the difference of these two will be considered as available moisture content to the plant, available to plant, not to anybody else, available to plant, plant available moisture. So this moisture is usable by the plant. If we see this on a graphical way, so if there is no moisture, we call that soil as a oven dry soil. So moisture content at that time will be zero. There will be no moisture. If we take a sample of the soil which remains in the atmosphere, it gets some water from the atmosphere, and that is called as a hygroscopic moisture, and we call that soil as an air dry soil. So air dry soil will have some moisture, so that is actually the hygroscopic moisture. It will be it will be bonded with the soil grains with the help of the chemical bond, although loose chemical bond, which can be taken out from the soil through oven drying method or by applying further soil tension. Between the oven drying soil and the field capacity, the moisture is considered to be the capillary moisture. And there is a line, or there is a small difference between hygroscopic moisture and the wilting point. So there is a small difference between these two. Sometimes we take them same, sometimes 5 to 10% we add in the hygroscopic moisture, and we say this is the wilting point. In the hygroscopic moisture, we add about 10% of that, and we say this is the wilting point. We should not let the soil moisture go below wilting point, because it will damage the soil yield. It will damage the output of the soil. And we should put that much moisture in the soil which bring the moisture content to the field capacity level or up to the maximum capillary moisture. So beyond that, any moisture, that will be called as gravitational moisture, and it will drain out of the soil under the action of the gravity to the deeper layer. So this graphical representation of these moisture content in the soil will help you understand how much moisture is needed. For example, when you apply irrigation, and if it is in excess quantity, maybe soil reaches to the saturation point. But in a couple of days, it will come to the field capacity level. And depending upon the evapotranspiration requirement of the soil, every day this moisture content will go down, will go down, will go down. You should plan your next irrigation when water reaches close to wilting point, not to the wilting point. So if I say this is the available moisture content, the difference between field capacity and the wilting point, so then usually we apply next irrigation when 80% or 70% of the available moisture content is utilized by the crop. So we will not wait for the 100% utilization of the available moisture content. So got it? So this concept need to be understood. That will help you in scheduling or application of water on scientifically basis, not on rotational basis or varabandi basis. We are applying water to the field in the irrigation system using the system we call as varabandi or rotational method. After a fixed number of days, a farmer get the water and he apply it to the field. So he don't see what is the condition of the soil. He don't see what is the moisture content in the soil. One thing is he don't have the instruments to measure these things. And second thing, he cannot apply the water when he need it. He has to apply the water when he get it, because we have a supply based system. When we have the water in the rivers and we supply it, we don't provide water on the demand based system. Our goal of a good irrigation system is that we should convert slowly towards a demand-based irrigation system. So in the demand-based irrigation system, so then this is the way how we decide on daily basis, on continuous basis. We keep the record of the soil moisture, and when the soil moisture reaches close to the wilting point, then we apply irrigation, and we apply that much irrigation which increase the moisture content to field capacity, not beyond that. So that is the concept we use in sprinklers also. That is the concept we should use in a scientifically based working irrigation system. So with respect to that, you should be knowing how to convert this moisture content into depth of water, because we are familiar with measuring the volume of water in cubic meter volume unit or in depth of water units. Depth of water, if you know how much depth of water is required, you can convert it into the volume by multiplying with the area on which that depth is applied. So multiplying area with the depth, you can convert volume, and you can convert, if you have the volume of water available, you can convert it to depth by dividing by the area on which you want to apply that volume of water. So to convert it into moisture content in theta into depth of water, we need a formula. This formula is required. Depth of water is equal to moisture content times depth of the soil into the specific gravity of the soil. G is the specific gravity of the soil. So its derivation, we want you to understand. We know this relationship of moisture content. Simple moisture content is ratio of the mass of the water to the mass of the dry soil. So theta is ratio of mass of the water to the mass of the soil. Similarly, we have the idea of the density. From the previous classes, we have the idea of the density. Density is the ratio of mass to the volume. So then there are different kind of the density. Then we have the density of water, which is the mass of the water divided by volume of the water. And usually density of the water is close to 1 kg per liter, or 1000 cubic meter per 1000 kg per cubic meter. Density have two kinds, there are different types of density with respect to soil. One density we call as the bulk density of the soil, and another one is called as the particle density of the soil. Bulk density of the soil is mass of the soil divided by the bulk volume of the soil, total volume of the soil. So if you take a core of the soil from the field, and you just measure the volume of that core, so that is the bulk volume of the soil. In comparison to that, if you dry that soil and then take the volume of the dry soil, so that will be called as volume of the solids. So if you calculate the density with respect to bulk volume of the soil, so that density is called as the bulk density of the soil. You just take the core from the soil, measure the mass of the solids in it, and divide that with the total volume of the soil. So that will be called as the bulk volume. It's a bulk density. Its usual value varies from 1.1 to 1.6 grams per cc per centimeter cube. As comparison to water density, water has a density of 1 gram per cc, or 1 kg per liter. So it has a density of bulk density of the soil varies from 1.1 to 1.6. As compared to that, if I divide the mass of the same soil with only the volume of the solids, so that will be smaller quantity. It don't have water in it. So then this density is quite high. Its value ranges from 2.6 to 2.7. In geotech, when you sometimes use that, or in concrete you use, you are using at that time this particle density 2.6 to 2.7 grams per cc. So we will be using this bulk density, and we will be calculating the depth of water using this bulk density value. So bringing that formula from the previous slide, bulk density is ratio of mass of the soil to the bulk volume of the soil. And similarly, we can write the density formula for water, mass of the water to the volume of the water. And the ratio of these two is said to be specific gravity, bulk volume of the soil to the bulk density of the soil to the density of water. And putting these three things, we will be putting in the formula of the moisture content. So moisture content is ratio of mass of water to the mass of the soil. So replacing this mass of the water with the density multiplied by the volume from this second equation.
इस बात को वो जत्था बुरा समझता, उसे दिल में बुरा जानने के बजाय बुराई के खात्मे के लिए जोरे बाजू का इस्तेमाल किया जाता, इखलाकी पुलिसिंग की जाती।
उमर फारूक, उमर फारूक को शर्म हया है तुम्हें? Okay. Umar Farooq, please see me or call me at 905. तुम्हें अलहदगी में तुम्हें कुछ कहते हैं। Okay, so moisture content, we know this relationship, mass of the water to the mass of the soil. So replace mass of the water with the density times volume of the water. We know this thing. Similarly, replace mass of the soil with the density of the soil into volume of the soil. So rho B into VB. So replacing this ratio of the rows with the G and replacing volumes with the area into the depth. Volume of the water is area on which that water is applied into the depth of the water. Volume of the soil is area of the soil multiplied by the depth of the soil. And usually this depth of the soil for measurement of the water we take as a root zone depth. So this both area will be cancelling with each other. The rest over term is moisture content is depth of water over depth of the soil into G. So by rearranging this equation, the depth of water can be said to be equal to product of moisture content times depth of the soil times specific gravity. So this formula is quite useful if you know how much moisture content you have to increase. If previously there is a 10% of the moisture at the wilting point and you want to take it to 25%, so it means 15% moisture content you want to add into the soil having a depth of let us say 1 meter or 1.5 meter root zone depth with the soil having specific gravity of so much. Specific gravity of the soil can be found from the density of the soil divided by density of the water. So if these things are known to you, depth of the soil and the specific gravity, of course it will come from the relevant soil. And if you know how much moisture content you want to add, you can calculate how much water you have to apply through irrigation. So that depth of water can be calculated. So this formula is useful for conversion of the moisture content. So a question has been given over here. So what is the quantity of the water required in depth unit if soil has a water deficit of 13%, water deficit of 13%. So he is telling you how much is the deficit. You don't need to calculate it. Sometimes we tell you that the soil is sandy silt soil or silty sand soil. So then from the literature we see what is the field capacity of this soil. We see what is the hygroscopic moisture content of this soil or wilting point of this soil. So that difference of these two moisture content is available moisture content. So we then decide whether we want to apply irrigation when 100% of this available moisture content is utilized or 80% is utilized. We keep some factor of safety and we apply before 100% is utilized. So then this moisture content deficit can be calculated. So if somebody tell you only the soil type, so people have carried out experiment on the soil types and have informed us your irrigation books will be having a table which will be telling you field capacity for sand, field capacity for loam, field capacity for clay. Similarly, they will be telling you hygroscopic moisture content for sand. So the difference of these two should be considered as available moisture content. So this deficit of the moisture which we have to fill is 13%. Other way is written in the brackets. For example, soil has a field capacity of 25%, and we want to apply irrigation when it reaches to 12%. So difference is 13%. So soil has a depth of 0.15 meter. That comes out to be ये कितना हो जाएगा? About 6 inches of the soil we want to soak, and it has a bulk density of 1.4 grams per cc. So maybe in your numerical, this value is different, so I have changed it a little bit. So for this depth, for this depth of soil, the depth of water required to fulfill this 13% deficit of the moisture will be moisture content 0.13, 13 divided by 100. 13% is 13 divided by 100, multiply by the depth of the soil, multiply by the G value, specific gravity value. You see in this formula, moisture content has no units, G has no unit, only depth of the soil has a unit. So this depth of water unit will be the same as depth of the soil units. If the soil is written over here in meters, the answer will be in meters. So multiplying these three things, we get the 0.027 meter of depth of water is required, which is equivalent to 2.7 centimeter. Close to 1 inch of the water is required to fulfill this 13% water deficit in 6 inch of the soil. Having a specific gravity of having a bulk density of 1.4. Bulk density and the specific gravity are same numerically. Conceptually, they are different. Bulk density is mass per volume, while specific gravity is ratio of the density, so no units. But numerically both are same because water has density of 1 grams per cc. When I calculate the G value, 1.4 divided by 1, so numerically whatever is the value of bulk density, same is the value of G for water having a density of 1 grams per cc. So numerically 1.4 will be the bulk density, 1.4 is the grams per cc is the bulk density of the soil. So that is why we are saying that bulk specific gravity is 1.4. So if crop area is given, so if somebody tell you that the soil on which we have to apply this water, it has so much hectares of the land, multiply that hectares after conversion of unit to the same unit, you will be getting the total volume of the water. If somebody tell you 10% are the losses, so add 10% into that, so that much water should be added. If somebody tell you that it has to come from a head regulator which is 100 kilometer, and then you add the losses, conveyance losses also. So similar is the question given over here. You are supposed to do it and then submit it. Wheat is sown in 1 hectare land with soil bulk density of so much. Wheat has root zone depth of 1.1 meter. Soil in this area has field capacity of 23% and wilting point of 10%. So now they are not telling you the water deficit. So water is scheduled once available moisture content depletes 80%. So calculate moisture deficit at the time of next irrigation. So that you can calculate by first calculating the available moisture content. So that is the difference of the field capacity to the wilting point. So 23 minus 10, 13% will be the available moisture content. And we want to irrigate when 80% of this is depleted. So 80% of this, 13% will be something 10 point something or whatever it comes to be. So that will be the that moisture content we have to fulfill. So calculate the depth of water for this 80% of 13%. So calculate volume of the water required. Now you, if area is given to you, 1 hectare land is given to you, you can calculate volume. If losses are given to you, you can add it further into it. Some more definitions you need to understand: crop period, base period. We have discussed this previously also. The total quantity of the water which is required by the crop during the whole base period, we use term delta for that. There is another term called duty. So duty is how much area can be irrigated by continuous supply of 1 cubic meter per second of water for the whole base period. So if we apply water continuously for the whole base period equal to 1 cubic meter per second, how much hectares we can irrigate? So that number of hectares will be called as duty of the irrigation water. Your time for today lecture is finishing. If you have no lecture after this, I can continue 5-10 minutes. If you have lecture, please tell me. CR, आपका लेक्चर है इसके बाद क्या नहीं है?
नो सर, ए सेक्शन का नहीं है.
ए सेक्शन का नहीं है, बी सेक्शन, डी सेक्शन का
नहीं है सर.
Okay, I will take just 5 minutes so that we can go to the next lecture with a new topic. So these concepts of delta is the total quantity of water in depth unit. So total quantity of water utilized by the crop or needed by the crop or that we apply to the crop in depth unit, that will be called as delta. It will be represented by centimeters or inches or feet. So you know it can be calculated by volume divided by the area. Duty is maybe a new thing for you, or in lab computation you are already familiar with this. If at a certain place you are supplying 1 cubic meter of water per second, discharge value is given for the whole base period, how much area can be successfully irrigated? So that is duty. Because there are losses in the system, so don't consider duty of the water will remain same at different places. Also, duty depends upon which kind of crop you are growing, which area you are talking about, depending upon their climatic condition. So duty is site specific, location specific, crop specific, cropping pattern specific. So, and it is depends upon location with respect to irrigation system. For example, duty at duty at the head of the regulator will be less as compared to duty at outlet. Bring in your mind the irrigation system. We are providing water from the river. It comes through the it comes at the head of the canal. Then it passes all along the main canal, then branch canal, then distributary canal, and then it reaches to the outlet. So if 1 cubic meter per second is supplied at the head of the canal, head regulator, it will incur some losses through the canal irrigation system. Then it will reach to the outlet. So it will be able to irrigate less land as compared to 1 cubic meter per second, which is available at the outlet. So duty at the outlet is more as compared to the duty at head regulator. Similarly, duty at the head of the field will be even more than the duty at the outlet. So duty varies from place to place. It increases as you move along with the irrigation system from head towards the tail. If you move from head towards the tail, duty value increases because duty is the area irrigated in hectares by a unit quantity of water, 1 cubic meter per second of water, if it is supplied for the whole. So because it is different at different locations, so people are using different names for this. For example, duty at the head regulator is sometimes called as full supply factor. इसी ड्यूटी को full supply factor कह देते हैं. Duty at the head regulator is called as a full supply factor, and the duty at the outlet of the canal is called as outlet discharge factor. So these are the other terms for the same thing, duty at the head. Variation of the duty with respect to location, you should understand this thing, this concept. You should not think duty is constant within the system. Duty is different at head, duty is different at outlet, duty is different at field because of the losses within the system. So duty reduces as we move from field towards the head of the canal. Duty reduces as we move from field to head of the canal. From field, we will be passing the water course, then we will reaching outlet, then going towards head, we will be passing through the distributary canal, then branch canal, and then main canal. So as we move towards the head, duty reduces. There is concept called, जी बोलो.
तो आपने रिवर्स में बोला कि अगर हम हेड से फील्ड तक मूव करेंगे तब ड्यूटी रिड्यूस होगी।
इंक्रीज करती जाएगी। हेड से टेल की तरफ जाएंगे तो ड्यूटी इंक्रीजेस, टेल से हेड की तरफ जाएंगे तो ड्यूटी रिड्यूसेस।
ओके सर।
Because definition says that duty is area irrigated by unit quantity. So when you say I am measuring the duty at outlet, so over there you will be supplying 1 cubic meter per second. So before reaching to the field, it will have less losses. So more water will be available at the field, as compared to if you release 1 cubic meter per second from head of the canal, which is sometimes 10 of kilometer away from the outlet. So 1 cubic meter per second will not be 1 cubic meter per second at the outlet. There will be some losses in between. So we cannot say 1 cubic meter per second at head will irrigate same land as 1 cubic meter per second at the outlet. ठीक हो गया?
Yes sir. Yes sir, समझ आ गई, thank you.
Okay. Similarly, we must be familiar with these intensities: cropping intensity, irrigation intensity. Maybe you are familiar in the laboratory part also. Irrigation intensity tells us how much area is irrigated with respect to the total culturable area, with respect to total area which can be cultivated. If, for example, we have 100 acre of the land and all the 100 acre of the land is irrigated, what is the other option other than irrigation? Other option is we don't provide water, or we use the natural precipitation. We call it rain-fed agriculture. So other option is this. So if 100% of the land is provided irrigation, we say irrigation intensity is 100%. If I apply 2 crops over there and I give irrigation water twice in a year, I will be saying irrigation intensity is 200%. So that is how concept of irrigation intensity is there. It is a percentage of the culturable area irrigated during a year. So if I irrigate it only once in a year, and if I irrigate 100% of the culturable area, then its value will be 100. And if I irrigate it twice, its value will be 200%. So it varies from less than 100% to more than 100%, depending upon how many crops are grown in that area. So it is related to the irrigation water supply to a certain area. Percentage of the culturable area irrigated. So if 50% area is not irrigated and 50% area is irrigated, and we are irrigating it just once in a year, irrigation intensity will be 50%. Originally, when this system of irrigation was developed, the designer kept in their mind 75% irrigation efficiency, irrigation intensity. Irrigation intensity was considered as 75%. They considered that we will be supplying once in a year, and we will be supplying only water to 75% of the culturable land. The rest of the land, they say they will get water at their own, or it need not to be cultivated, something like that. So originally it was 75%, but with the passage of time, people have brought more area under irrigation by making area plain through bulldozer. They are making the area bringing the area under irrigation. They are putting the tube wells installed over there, so that area becomes also under the irrigation. So nowadays irrigation intensity in Punjab is said to be close to 150%, and in some parts especially it is more than this. Similar to irrigation intensity, there is a concept of cropping intensity. So that is related to how much area is under crop out of the total area, out of the culturable area. So if there is an area, for example, total is 100 acre, and out of that 75 acre is culturable area. Some area is not culturable, cannot be cultivated. For example, if there are houses, if there is a road, if there is a water pond, so such area are considered not culturable. So we have to, from the total command area, we have to subtract that area. The remaining is the culturable area. If all the culturable area is cultivated by the farmer, once in a year, its its cultivation intensity or cropping intensity will be said to be 100%. If we grow 2 crops in all the cultivable area, we will be saying its cropping intensity is 200%. And most of the area in Punjab are getting more than one crop, so we are close to 200% cropping intensity. It is the percentage of the area cropped with respect to the cultivable command area. So percentage of the area cropped with respect to cultivable command area. So if only one crop is grown, it will be 100% or less than 100% depending upon how much area is cultivated. If more than one crop is grown or more than 2 crop is grown, its value can be higher. So more than, if we are growing 3 crops, small crops, 3 month, 3 month, 3 month, so it can go beyond 200% for certain area. So cropping pattern is representation. I think I discussed it earlier also. Cropping pattern is representation of area under various crops, percentage area of the land under various crops in a season or in a year in a canal command area. So in the area of our interest where we are studying, where we are working in a canal command, how much area is cultivated by one kind of land, how much area is cultivated by other kind of the crop. So that is called as a cropping pattern. So that looks something, it is not given over here. So cropping pattern will be, for example, I tell you wheat is using the 35% of the cultivable command area. Grams are using 10% of the area. Fodder is using 5% of the area. So similarly, if I provide you the area of Kharif crop and annual crops also, so that will be called as a cropping pattern. So it is a table or it is a schedule of percentage land under different kind of crops in a certain area. So there is a question, numerical, which is solved also over here, but you have to try to solve it yourself using the concept just given to you. For find the volume of water required if cultivable area is 65,000 hectares. From the following data, water losses may be taken 16%. So area of the land is informed to you, and this land don't have only one crop, it has 3 different crops over there. For example, in Rabi we have the wheat crop. You should be now familiar with the name of the crop and its season. So you should be familiar that in Pakistan wheat is grown in Rabi season, while rice is grown in Kharif season, and the sugar cane is the annual crop. So total quantity of the water we can calculate. Then we can calculate the water requirement in the Rabi crop and water requirement in the Kharif crop, and also we can take into account the losses over here. So B in days is B is the representation of the base period, and I think we have seen the definition of the base period and the crop period, or we went ahead of it. So base period was the time in days from first watering to the last watering to the crop. So base period is the time in days from first watering to the last watering, while crop period is the time a crop takes from its sowing to the harvesting. So there is a small variation, small difference between these two definition, base and crop, but for us they are nearly equal to each other, because immediately after sowing we have to give the first watering. Immediately after sowing we have to give first watering, and a few days before the harvesting we have to give the watering also. A week or 2 weeks before we have to give the last watering. So they are theoretically different from each other, crop period and the base period. Crop is from sowing to harvesting, base period is from first watering to last watering. So this base period is more utilized in irrigation. This crop period is more utilized by those people who have to plan the next crop, who has to plan the cropping pattern in that area. So we should be familiar. I think I left this part. Where is that? Conversion of delta into duty. We know that delta is the total quantity of water. which is applied to the land for a certain crop in depth unit. And duty is the area. Remember this, duty units will be area. When somebody say duty, he will be telling 2000 hectares is the duty. He will be telling 100 hectare is the duty. So duty is the hectares of the crop being irrigated by 1 cubic meter per second of the water for the whole base period. So if you know the discharge and if you know the whole base period, B, days, you can convert it into the volume, and D is the hectares. So if you divide that volume by the D hectare, conceptually what will be the left? That will be the depth of the water required by that crop. So that is how this duty and delta are related with each other. From the concept of the duty, if I multiply 1 cubic meter per second with B days, 1 cubic meter per second with B days, by applying the conversion factor of days into seconds, 24 hours, 60 minutes, 60 seconds. So that is a conversion factor. So volume of water for 1 cubic meter per second supplied for the whole base period will come out to be 86,400 B cubic meter. Got it? So if this is applied, this much volume of water is applied on D hectares. So then I divide this volume with the D hectares, volume divided by area, this volume by D hectares. Multiply it with the 10 to the power 4, this will be cube meter square. 10,000 meters square are there in a hectare. 10,000 meters square are there in a hectare. Or 10 to the power 4 meters square are there in a hectare. So conversion of D hectares into meter square, we have to multiply with the 10 to the power 4 in the denominator. So then converting these two, we can find the formula of delta is 8.64 B over D, while B is in days, D is in hectares. So then delta will be in meters. So if I multiply it with 100, I will be getting delta in centimeters, keeping B in days, D in hectares. So this is the conversion formula for conversion of the delta, conversion of the duty and the base period into delta. Please remember it and try to solve this question. Also find the delta of the crop when its duty is 864 hectares per cubic with base period of 120 days. Similar formula but with different coefficient is there in FPS system. So in FPS system, duty will be defined as area in acres which can be irrigated by continuous supply of 1 cubic of water for the whole base period. Definition of the duty in case of FPS system, because units will be changing. So over there, unit quantity of the water will be 1 cubic, not 1 cubic. And it will be the and area will be in acres, not in hectares. So because of this variation, so conversion of the delta into duty into delta will be can be calculated in the similar way, but not with the same coefficients. Coefficient will be varying. Please try to find that one also. Using the same concept, convert the 1 cubic into volume of the units in cubic feet, then divide it by D acres, convert acres into square feet, and you know 1 acre is 43,560 square foot. That will be the instead of 10 to the power 4 over here it will be 43560. So then your delta will come out to be in feet. So if you multiply that with 12, your delta will be coming in inches. So please try to find the formula for delta and duty in FPS system also. In field, FPS system is used more commonly. So this concept, if we know, then we come to this problem. So base period for each crop is given. Duty for each crop in hectares per cubic is given. How much area is under the crop, area of irrigation, intensity of irrigation. So 15% area is under sugarcane, 20% area is under wheat, 10% area is under rice. 10% of what? 10% of this 65,000 hectare. 20% of 65,000 hectare, 15% of 65,000 hectare. So area is known, duty is known, B is known. So the methodology will be find the depth of the water or delta of the water required for sugarcane, for wheat, and for rice by using the formula of delta, which is 864 B over D. Answer will be in centimeters. So then you can find the delta for sugarcane, multiply that with the area, so 15%, 15 divided by 100 into 65,000, you will be getting the total delta required for sugarcane. Similarly, do it for wheat, do it for rice, and you can add them together and you will be finding the total volume required if you have to, if you need this volume together for the whole year. So that is how it is done over here. Delta for sugarcane, delta for wheat, delta for rice. Then area is computed, and they are computing area in hectares. Then volume they are finding not in cubic meter, they are finding volume in hectare meter. Like we have the acre feet, in SI they are using hectare feet, hectare meter. So total quantity of water required is sum of all of them, add losses into it, and you can get the total volume required for this system of agriculture. In addition to that, the part which is not done over here is find discharge required during Rabi. So if somebody want to find the water required during Rabi, see which crops are there in the Rabi. So add water of the wheat and during Rabi, because sugarcane is a whole year crop. So in Rabi also it will be present. So calculate the water required for the sugarcane during the Rabi month. So take 6 months for the Rabi, or take half of this time period for the Rabi and half of this time for the Kharif. So half of the water will be required in the Rabi, half of this sugarcane water will be required in Rabi and half in the Kharif. So adding wheat plus half of the sugarcane will tell you the water required in Rabi. Adding rice and the half of the sugarcane approximately gives you the water in Kharif. In this way, you can calculate on seasonal basis. Further, in your lab class, you might be, this is seasonal and annual working, but in lab class, maybe you have to work on 10 daily basis. So then your water requirement should be calculated on 10 daily basis. Then evapotranspiration requirement on 10 daily basis should be known to you. Rather than this duty and delta, you should be knowing ET for each 10 days, depending upon temperature or evaporation values, you can calculate that. So over here it finish this part of soil water plant relationship. We have to give you some terminology. We have given you some concepts of how much water can be stored in different phases of moisture content, hygroscopic moisture, field capacity moisture, and from there we have given you the concept of available moisture. Then we have told you that out of the total available moisture, try to irrigate when 80 or 70% of that moisture is depleted. Don't wait for 100%, because in this irrigation system, we don't have surety that we will be having water when 100% is depleted. So try to keep some factor of safety and apply water before reaching to the wilting point or reaching to the lowest value. So you have been given the concept of water scheduling using demand-based irrigation. Some basic factors. So these full supply factor, outlet factor, base period, crop period, delta, duty, these are very commonly used in irrigation. So please comprehend them. Please try to understand them. Parallel to duty concept, there is another concept of using of water in Pakistan, India. We call that concept as water allowance for a canal. So water allowance for canal is the cusics of water which are allocated for irrigating 1,000 acre of land. Cusics of water which are given to a canal for irrigating 1,000 acre of the land. So that also gives us the idea how much water is being utilized for a certain fixed quantity of land. So in Pakistan, this water allowance concept is more frequently used as compared to the concept of duty. So water allowance for different canal varies from 3 cusics per 1,000 acre to 9, 10 Q6, and in Sindh province it reaches to 12, 13, 14 Q6 per 1,000 acre of the land. Depending upon soil type, depending upon climate condition, water allowance is different in different canal system. So that is crop water requirement. Please try to comprehend it and understand it. If you have any question, you can ask me now or later on. So if any idea, question comes in your mind, you are welcome. I am taking attendance. You can ask me the question.
सर
जी बोलो.
सर जो आपने न्यूमेरिकल सॉल्व किया लास्ट न्यूमेरिकल, तो उसमें जो आपने शुगर केन का वाटर होता है रबी और खरीफ में इक्वली डिवाइड किया है.
Approximately equally divide किया मैंने. Actually, if you know how many months of the Kharif are used, how many months of Rabi are used, then with that ratio you can calculate it.
स्टिल सर अगर मंथ्स पे भी देखें तो उसमें अगर खरीफ सीजन में ज़्यादा पानी नहीं चाहिए होगा बिकॉज ऑफ समर सीजन या इनिशियल क्रॉप रिक्वायरमेंट में.
You are right. क्या हमारे पास वो वेरिएशन है? हमारे पास इस क्वेश्चन में वो वेरिएशन मौजूद नहीं थी. Theoretically you are right. It is temperature dependent. It is dependent upon the crop period. It depends upon their growing period. ठीक है? तो उस लेवल पे इस क्वेश्चन में हम गए नहीं है. Download attendance list. So I have downloaded the list. I will put it on the WhatsApp. So if anybody have question, welcome. Otherwise, you are allowed to leave. I stop the recording. Thanks.